Hello, Math Universe. I'm making this video for my subs who care about math and physics. Read this book. Yeah, this book is insanely legit. Insanely legit. I don't even want to spoil it, but let's just say it derives electrodynamics from a Clifford algebra approach. Provides geometric intuition, but maintains the tensorial form of Maxwell's equations using the algebraic structure of the Clifford algebra. And no, I have not read this book completely. Most of the books I review, I try to have at least read them, or at least read significant sections. I've read like chapters 1 and 2 of this textbook, I think, in depth, and I've kind of skimmed. But even chapter 1 alone, I was like blown away. And yes, I'm definitely gonna be studying this for my PhD because it's highly related to the concepts that I'm going to attack. Yeah, I would just highly recommend this to anyone that actually cares about math and physics. Even if you just care about math, you should definitely read chapter 1 of this book. Put you on to some math that you need to know about and you need to care about. Vectors. Oh, what is a vector space? Well, what do we know how to do about vectors? Well, we can add them. That's pretty much it, right? We can scale them and add them. We know how to add vectors. Well, guess what? There's this thing called the Clifford algebra, which lets you multiply vectors. And it's related to the tensor algebra. Basically, you just take the tensor algebra and you quotient out by the ideal, by a very specific ideal, namely the ideal generated by elements of the form v tensor v minus identity times q of v, where q is a quadratic form. Okay, so you tensor out by that the ideal generated. You tensor out the tensor algebra. You you quotient the tensor algebra. Whoa, you don't tensor the tensor algebra. You quotient the tensor algebra by the ideal generated by elements of the form. Wait, let me just show you. Just explain this. Okay, sorry, 1 second. Okay, so you take the tensor algebra, which I'm going to denote by TV, or I guess T. Yeah, V. TV, okay? Where V is vector space, what is this tensor algebra? This is just the direct sum over T tensor K V. K goes from 0 to infinity, okay? So this is an algebra. It's equipped with the product of tensor multiplication, okay? And namely, yeah, we have this tensor algebra. You can look it up and research it if you want. It's called the tensor algebra. It's kind of a big deal. And then essentially the Clifford algebra, you essentially take this tensor algebra, TV, and you quotient it by the ideal generated by elements of the form elements of this form, where B basically I is, or no, not I, 1. 1. 1 is just the identity element of the tensor algebra, right? Because we have multiplication, you tensor something by 1, you get itself. Okay, tensoring by a constant, just equivalent to multiplying by that constant. So this is such that V is an element of the vector space. You quotient out by this ideal, and this gives you the Clifford algebra, okay? Turns out that where Q, by the way, is a quadratic form. Okay, so it turns out you take the tensor algebra of a vector space, you quotient out by this ideal, you get what's called the Clifford algebra, okay? Also, for those of you who took manifolds and you know about the exterior algebra, okay, interestingly enough, if you take the tensor algebra and you quotient by just the ideal of the form v tensor v, okay, such that v is an element of your vector space, you quotient out by this ideal. This is literally the freaking exterior algebra, okay, the exterior algebra, which is used the exterior algebra of differential forms. That's the algebraic structure of differential forms, okay? So, yeah. Pretty powerful stuff, actually extremely freaking useful. It turns out there's a full geometric interpretation of the Clifford algebra which is not from this algebraic standpoint that I just showed you, but from a geometric standpoint, okay, a highly geometric standpoint, which garners geometric intuition, really boosts like a ton of intuition about geometry, about three-dimensional space, about physics, about what the tensor algebra does, and kind of the geometry of tensors. And basically, William E. Baylis breaks down electrodynamics and does electrodynamics from a Clifford algebra approach, okay? So he sets up the Clifford algebra mathematically in chapter 1. If you only care about math, you don't care about light or electrodynamics, like you don't care about physics, then just read chapter 1. But if you care about physics and light and electrodynamics, then just read this book. I haven't even fully read it yet, but I definitely plan to read it. Most of the books that I review on this channel, I've read more than just a few chapters, so I apologize for that. But even from the 2 chapters that I've read, I can already recommend to you this book and put you on, and I promise you that it is worth your time. And I literally, this is going to blow your mind. So it literally blew my mind after reading the first 2 chapters. And I kind of got the picture of, okay, yeah, I didn't fully study this book yet. This book I 100% plan to study for my PhD. You take Maxwell's equations, which are tensorial in nature. That's a whole point. They're like invariant under these Lorentz transformations. It's kind of the motivating reason for the geometric structure of special relativity and Minkowski space, right, is this Lorentz symmetry, which is obeyed by the Maxwell's equations in their tensorial form. Well, but often electrodynamics is taught from either from a calculus 3 perspective, which is not tensorial, or from a tensorial perspective, but a lot of the intuition gets lost in the juggling of indices and just learning how to manipulate tensors. So what William E. Baylis attempts to do in this book, as he stated, is he attempts to present Maxwell's equations from the tensorial perspective, but motivate it geometrically using the Clifford algebras. And I really respect that. I think that's really important. And I 100% plan to read this book for my PhD because it's highly related to what I want to study, which is essentially optimal transport / electromagnetism / special relativity / numerical simulations. So yeah, I would highly recommend this book, and I hope you have a wonderful day.